insect crawling on a rough hemispherical surface. We have to find the height up to which an insect can crawl. An insect can crawl up. An insect can crawl up a fixed bowl. In the form of a hemisphere. Height up to which an insect can crawl up a fixed bowl in the form of a hemisphere. So this is a hemispherical surface or hemispherical bowl. O is the center of this hemispherical bowl, and we can draw a vertical radius. OA is the radius of the hemispherical bowl. An insect of mass M is at the point A. This is the insect. An insect is at the point A. The insect has mass M, and in this case, the insect crawls up the hemispherical bowl from the point A to B. The insect travels from the point A to B along the hemispherical surface or hemispherical bowl. Finally, the insect reaches to the point B, and at the point B, the weight of the insect, that is the weight mg, will be acting vertically downwards. Mg is the weight of the insect which is acting vertically downwards. We can draw another radius, that is OB. OB is the radius of this hemispherical bowl. Now the weight mg, weight of the insect, that is mg, is resolved into two rectangular components. The radius OB makes an angle alpha with the vertical radius OA. And in this case, if the weight of the insect, that is mg, is resolved into two rectangular components, then we get this angle will be again alpha. Because here mg cos alpha is the rectangular component of weight of the insect which is acting perpendicular to the hemispherical surface, and mg sin alpha is another rectangular component of weight which is acting tangentially at the point B along the hemispherical surface. The insect has a tendency to slide down. That's why limiting friction FL will be acting at the point B up the hemispherical surface and along the tangent. And we can denote the normal reaction on the insect applied by the hemispherical bowl at the point B. R is the normal reaction on the insect at the point B, and we can denote two radii. OA is vertical radius, that means small r is equal to OA, and oblique radius is OB, which is also equal to small r. Now we can draw a perpendicular from the point B on the vertical radius OA. This is the perpendicular from the point B on the vertical radius OA of this hemispherical bowl. Let an insect of mass M crawls up. Let an insect of mass M crawls up from the point A to B. Along the hemispherical bowl. Such that the insect rises through a vertical height. H. We can denote the vertical height rises by the insect, that is AN is equal to H, is the vertical height raised by the insect or reached by the insect. And in this case, vertical height is H, which is equal to AN. The insect at the point B on the hemispherical bowl will not slide down along the hemispherical surface. The insect at the point B will not slide down along the hemispherical bowl if the limiting friction Fl at the point B, which is acting tangentially upwards, in this case limiting friction Fl will be equal to the rectangular component mg sin alpha, where Fl is equal to mu into r, which is the limiting friction acting between the insect and the hemispherical bowl, and r is the normal reaction on the insect applied by the hemispherical bowl, or comma mu into r is equal to mg sin alpha, at the equilibrium, normal reaction r is equal to mg cos alpha, or comma mu mg cos alpha equal mg sin alpha, or comma mu equal tan alpha, where alpha is the angle subtended by the oblique radius OB with the vertical radius OA. Mu is equal to tan alpha. Mu is the coefficient of static friction between the insect and the hemispherical bowl. Mu is equal to tan alpha, which is the coefficient of static friction, where alpha is the angle between the oblique radius OB and the vertical radius OA. Alpha is the angle between the oblique radius OB at the final position and the vertical radius OA at the initial position of the insect on the hemispherical surface. Now, height raised by the insect is h, which is an equal to OA minus ON, equal r minus OB cos alpha, which is equal to r minus r cos alpha. R is taken common, under bracket 1 minus cos alpha. H is equal to r bracket open 1 minus cos alpha, which is the height raised by the insect along the hemispherical surface, where r is the radius of the hemispherical bowl or surface. H is equal to r into 1 minus cos alpha. As coefficient of static friction mu is equal to tan alpha, that's why we can say that as tan alpha is equal to mu, and that can be written as mu by 1. In that case, cos alpha is base by hypotenuse, which is 1 divided by root over mu square plus 1. As tan alpha equal to mu, then cos alpha is equal to 1 divided by root over mu square plus 1. So finally we get the expression of height raised by the insect h, which is h equal to r 1 minus 1 divided by root over mu square plus 1. H is the height up to which insect can crawl along the hemispherical bowl. Therefore, h, which is the height raised by the insect along the hemispherical bowl, is equal to r bracket open 1 minus 1 divided by root over mu square plus 1.